I wanted to review a statics problem that I typically do at the beginning of the semester for reviewing shear and bending moment diagrams. So I'm going to do a relatively simple beam. I don't know if you've done one similar to this. I kind of call it the coat hanger problem, and you'll see why here in a minute. Alright, so our givens basically is going to be a layout of the system we're solving for. So we have beam, we can call it A, B, C. I could have probably made that more to scale, but we'll leave it as is right now. We have a force being applied. This is why I call it the coat hanger problem. It kind of looks like a coat hanger. But we have a force that's being applied here at 100 pounds. We're going to have, I should have drew this out again differently. We have our pivot there at A, and the roller here at C. So basically, there's no horizontal forces, right? Alright, the other thing that we are given is that this leg of the beam is going to be 5 feet, and this leg of the beam is 3 feet. Like I said, it's not necessarily to scale. I'll try to draw that better when I do my shear or free body diagram. Alright, so we have the problem laid out. And what we want to find, our reactions at A, reaction at B, and reactions at C. We also are going to want the shear diagram for beam ABC. So this beam right here. And we want to get as well the bending moment diagram. Again for ABC, that beam. Alright, so that's what we're looking for. Our solution is going to be basically, well, first thing we do with this, I would always draw out my free body diagram, and or multiple free body diagrams if it requires it. Like this one, we have a multi-body problem, right? Because what we have is a beam ABC, which is what we want to solve for. But we also have this extra leg over here that's going to be adding a moment at B, as well as a reaction force here at B of 100 pounds. But there's also going to be again that reaction moment. And yeah, we could solve for reactions at A and C without basically thinking of this all as one part. But again, that doesn't help us when we're trying to really solve for forces and bending moment diagrams within beam ABC. So we have to basically break this part. So what we're going to do is we're going to have two free body diagrams. The first one, so I'm going to label one here. So we have a force of 100 pounds. The reaction here at B, well, it's going to be 100 pounds, right? There's no other forces there. I'm going to write that, but I'm also going to write out the equilibrium equations here. But I'll show why we can kind of say that that's 100 pounds. And then we're also going to have a moment here. And I'm going to call this one moment B. And I drew it this way because if you look at how the forces here are going to rotate this, we'll end up doing this pivot, right? Well, we need to counteract that because statics, everything equals to 0, right? So if this is causing a pivot this way, we have to have a counter pivot or counter moment, right? So that's why I chose that direction for moment B. And we can actually calculate. We'll see that if you weren't sure, for instance, what that moment is or which direction, you can actually use your equilibrium equations to help you with that. So I'll explain that here in a minute. To do so, I realized I forgot one other measurement here. So we have to have that 1 foot in order to be able to figure out what this moment is, right? All right, so first thing again I do after I get my free body diagrams drawn is I go through equilibrium equations. And I think I should probably finish drawing out my free body diagrams here, and I'll do that. So we have reaction at A, a reaction at C, as again, I typically, if you're unsure of which direction to point the arrow, I would always point it up. So I'm gonna just do that this time to show you what happens if we assume it's up. Reaction at B, and then we're gonna have some sort of moment, right? And again, always assume positive. So if you're unsure what that moment's gonna be, you can assume it's positive. And then if it happens to be the other, we can flip it around the opposite direction. So I'm going to assume positive here. I'm just going to write it in. Oops, moment B. And we will have to go back and fix that. So let me go through this one first, and then we'll go through this, write out our equilibrium equations, and solve. So first thing, equilibrium equations for this, well, f of x summation is going to be equal to 0, right? There's no horizontal forces. Vertical forces in our y direction, what we see, we have a negative 100 pounds because it's going down, right? So minus 100 pounds, negative x direction. And then we have plus positive 100 pounds, right? Well, plus RB. I already assumed 100 pounds because I could tell what, there was only one other force, right? But in this case, we could just show this, and then, well, reaction at B is equal to, let's go to the other side of the equation, would be a positive 100. So there's reaction at B. And then summation here of our moments for free body diagram 1. So all the moments will end up equaling 0. But what we do have is, well, so we have to pick a point, right? So think about where we're going to be pivoting around. So our summation of moments here, really around B. And what we're going to have is 1 foot, our first moment, right? 1 foot, absolute bar 1 foot times, this is why we do absolute bar. So if you put a negative 100 pounds in, for instance, since it is a negative force, it'll still be positive if that moment's going to be positive. So is this going to be positive? And this is where you have to do right hand rule. So again, if we do right hand rule, my way of doing right hand rule, or thinking of it and explaining it, is you think of the axis along your palm, and then I curl my fingers in the direction of the force. So the force that would be essentially causing that moment, and F would cause this curl around, right? Thumbs has to point into the page to do that, so we get a negative moment there. And again, we always use absolute value bars because, again, if this was a positive moment, or say a negative moment, but it created a positive moment, we don't necessarily want to get a negative if in fact it is a positive moment. So that's why you always use right hand rule for figuring out, if the moment's going to be added as positive or negative for summation of moments. We'll actually talk about beam and bending here actually later on in this video. But so summation right hand rule. So in this case it was negative, and then what we're gonna see is, again, we assume positive, right, for our moment at B. So we have this leftover moment. We have to equal 0, right? So we can't just have a moment here with no equalizing moment. So we end up finding our moment at B is equal to, well, if it's negative, we bring it to the other side of the equation. We'll get a positive. Absolute value bars, again, cancels the negative inside. And we get 100 pounds, or pound feet, right? Pound foot, foot pound, pounds times feet. All right, so we have our bending moment for MB. And now we go look at free body diagram 2. We've got everything we can get out of free body diagram 1. We now know our reactions here, so again we've solved for RB now, and we have our moment MB, which is going to be 100 pound feet. Okay, so we have that. Now we have to bring it over to this one, right? And if you remember, when you break up free body diagrams at the same point, so our point B here and our point B here, we're going to get equal but opposite reaction forces as, say, we look at going from one free body diagram to the next. So since we know we have a positive 100 pounds here, we're actually going to have a negative reaction for B there. So we'll actually have that be 100 pounds downward. So that changes direction. And then for moment B, again, equal but opposite here, that flips. So the neat thing here is why it's saying if you always assume positive, when you actually plug it into the equation and see that you're, say you have an arrow pointed downward, you get a negative, it's supposed to be pointing positive, but that can be kind of confusing. So you always assume positive and get a negative. You just know you need to flip the arrow. So in this case, RB would have been negative, so I just flipped the arrow. You could put negative in here again, but I lay out my forces as kind of like an absolute value, and then the arrow kind of depicts the positive or negative direction. That's the way I like to do the free body diagrams anyways. So bending moment here, again, equal but opposite, so this has to swap directions. And it makes sense if you think about the direction that F force is going to cause this to spin. So if we look at how that's going to want to make this pivot, well, it's going to cause this moment here at B, right? So you're going to get this kind of torque or moment here right at B due to that force. So we know it's supposed to be essentially a negative moment, right? So positive here to counteract this negative moment, and this one's negative to basically, when we flip, it's equal but opposite. All right, so now that we have this free body diagram drawn out, we know our reaction forces in the center anyways. Now we need to get our reaction forces on either support. As I mentioned, this is 100 pound feet. And again, it's going negative direction now. So first thing I do, again, lay out my free equilibrium, 0. So for X, no horizontal forces. Vertical forces for Y, well, I'm just going to go from left to right. So we have our reaction at A minus our reaction at B plus our reaction at C. And I know we have a moment in here, but this is not a summation of moments, right? So we have only our forces. The next one is our moment for summation of moments for free body diagram 2. And at this point, for the beams, what I like to do, well, first I go through, are there any moments on the beam itself? You know, do we have any of these moments on the beam? If so, we add them. So moment at B, and again that's negative, right? So we have to add a negative in front of that. All right, and then we have plus absolute value bar, and then the force times the distance, right? So this was 5 feet. This one was 3 feet between these two. And then we have our reaction at B times that 5 feet. I don't know why I should have put the forces. I'm just going to write feet. Just write it as this right now. And then we have positive. Actually, that should have been negative, right? So right hand rule causes a negative moment here to reaction at B, make you want to pivot, thumbs into the page, right? Alright, so that was supposed to also be negative, and then plus this one is positive. So we have RC times 8 feet. We again I kind of point my fingers in the direction of the force, my thumbs pointed up so that along the axis of pivot, so we end up getting a positive moment. Alright, and at this point we have our knowns and unknowns we can plug in and solve for our unknowns. So the thing we want to do, well, we know we have moment at B, we have reaction at B, right? We just don't have RC. So the first one we're going to want to solve for is our moment, and I usually like to put in 0 equal to 0 over here. Kind of out of space there. Alright, so this one, 0 is equal to negative 100 pound-feet. Minus absolute value bar, reaction of B. So we had negative 100 pounds times our 5 feet plus RC, which we don't know, times 8 feet. Again, absolute value bars. Sorry, I'm getting a little crunched there, but basically that's just so you can read it. This is RC plus 8 feet. This is a problem with working with pen. Alright, so we want to get RC by itself on its own side of the equation. So since all these others are negative here, we'll just bring those to the other side of the equation. So we have RC times 8 feet. One side of the equation. The other side will have a positive 100 pound-feet plus, because we're going to bring it to the other side. Negative 100 pounds times 5 feet. Alright, again, sorry, getting a little crunched there. So now we just divide through by our 8 feet. I'll rewrite that whole thing so hopefully you can read it. 100 pound foot plus absolute value bar minus 100 pounds times 5 feet absolute value bar, all divided by 8 feet. All right. So we have 500 pounds, right? 5 times 100, and we have 100. Well, 5 times 100, or negative 100 rather, is a negative 500, but absolute value bars is going to make that a positive 500. So we end up getting 600 pound-feet divided by 8 feet. So RC is equal to, well, get the calculator out. 600 divided by 8, 75. And that's in pounds, right? So our feet cancel, we're left with pounds. So RC, 75 pounds. Now we just need to find reaction at A. And we already have reaction at B. So all we really need to do, and I think I'll just draw kind of a line there so we know which ones I was solving for. We're running out of room. But we would want to use this equation. 0 is equal to reaction A minus reaction at B plus the reactions at C. Alright, so we're looking for, in this case, reaction at A. So we want to bring everything else to the other side. So reaction at A is going to equal a positive RB minus RC. Reaction at B, 100 pounds minus reaction at C, 75 pounds. Reaction at A is then 25 pounds. I think it makes sense that reaction at C is going to have a higher reaction force than reaction at A because we have this pivot, right? So this beam is going to be pushing harder on RC than it will be at RA. So in some cases, if you get enough of a moment, you could be potentially trying to hold down here at A and get a negative force there. But in this case, it was 75 on this side, 25 on this side, as far as the weight in pounds. So that gives us our reaction forces. Now we know, what our reactions are in each place. So the next step here is drawing out our free body diagram. Or sorry, not free body diagram. I do that again, but the shear and bending moment diagram. So as I said, first thing I do for the shear and bending moment diagram is redraw out, because you're using your free body diagram to actually draw these. So we have reaction at A. This was, as we said, 25 pounds. Reaction at C, 75 pounds. Our reaction at B was 100 pounds down, and a moment that was clockwise negative, right? 100 pound-foot. And again, we have our 5 feet here and our 3 feet here. Again, this is really being able to solve for the reactions here at B and then get the full analysis for shear and bending moment diagrams here is really why you have to break these apart. So for our shear diagram, draw the beam. I like to Gonna draw a correlation so I can kind of see what points. And we have, well, positive 25 pounds here, so we're going to go up 25 pounds. And that 25 pounds is going to hold until we hit this downward force. That's going to take us down a whole 100. Well, if it's 25 pounds here, then it's going to be a negative 75 pounds here. And then we have that positive 75, brings us back to 0. So we know we've done that correct. We wound up at 0. If we're not at 0, we're not in equilibrium. It's not correct. The only thing I like to do for these is I like to, that's supposed to be a V, shear. Shear diagram in pounds. And then our bending moment. Carry dots down. Alright, so bending moment diagram. You guys are probably used to the areas here. Like you find the area, right? 25 pounds times your 5 feet gives you how much of a rectangular, that slope you get, right? And where you're going to end up by the time you end up getting to point B. So we find the area, which is 25 pounds times 5, which would give us 125 pound-feet. And then for this one, we have 3 feet times 75 pounds gives us, in this case, a negative because we're underneath the x-axis, right? So we're going to get a negative slope to our moment. That's going to equal negative 225 pound-feet. Alright, so starting off, as I said, if we're above the x-axis, we'll have a positive slope, rectangular, kind of rectangular shape here. So we're going to slope up, and we're going to get to, this is going to be our point, 125 pound-feet. And once we're at B, this is where this other moment comes in. And the odd thing here about adding moments into your bending moment diagrams during this here is you got to think of the bending moment rule. So there's a beam and bending rule. The beam and bending rule states that basically depending on how the beam is shaped, how it gets contorted, essentially depicts whether it's positive or negative. So for instance, in this case, just draw here. Actually, I'll leave that out. So I'll draw the beam again. We have our beam A, B, C, and we have this moment, right? That moment here is going to cause this beam to want to basically flex like that, and this side will flex up. So you'll end up getting this kind of flexing of the beam. So beam and bending states that when you have a beam that's bent this way, we end up getting a positive, and when we have a beam this way, we get a negative. And kind of the funny way of remembering that is, well, if it looks like a smiley face, it's positive. If it looks like a frowny face, it's negative. So when we look at this, our pivot's going to do this, which is going to cause this to want to bend, right? And we always look at where we're moving to when we're going from our bending moment diagram. Moving right, we look at the beam and bending. All right, well, we see it's going to give us a positive beam and bending, right? So we're going to add this moment for the positive beam and bending, and that gets added. And it's just going to go straight up on the bending moment diagram. So we just add the 100 pound-feet. Then our max bending moment here is going to be at, well, 125 plus 100 is going to give us 225. And then, as I said, for this last portion, our area is underneath the curve. So we just subtract that area, again, at a slope in the negative direction because we're below the x-axis. And again, this brings us back down to 0. We are at positive 225, and then we subtracted 225 from that, brings us back to 0. And we got our bending moment and shear diagrams. So bending moment, I like to put M for a bending moment diagram and state the units we're using, pound-feet. But that's really the kind of the summary there for the full problem. If you have any questions on how I did that, let me know. But this should be probably one of the only new things, I would say, adding a bending moment within your beam. I believe I've been told by students in the past that Jeff hasn't really done problems quite like this, and I'm sure he lays out his statics problems slightly different as well. But that gives you an idea of how I do things, I guess, and this beam and bending stuff here, rather important, especially when we start getting into stresses that are being applied on a shaft, drive shaft, for instance, that might have multiple different gears. So you're going to have various different forces. Maybe you have a spur gear or something that's going to have also like a moment that's going to be applied onto your drive axle or something. So this is where it comes into machines. And by the end of the semester, we'll be doing basically analyzing a drive axle, basically, or drive shaft with various different either gears, bevel gears, or spur gears, or we'll do belt drives or chain drive systems. So we'll go through those. But this is the kind of forces you think about. Right, what kind of force does a chain put on my system, and how is that applied? Thinking of it as simple as possible as a beam. So that's typically statics. You're wanting to simplify your design for analysis, and then figure out, all right, where are my max stresses? And then what we do by the end of the course is we take this and correlate it to a finite element analysis. So again, that gives you an idea, and what I'd like you to do is go through the whole problem, write it out neatly. I would try to avoid this kind of stuff. Tried to, but obviously you can only do so much with a pen or a marker in this case. But again, let me know if you have any questions or issues, or just need a little bit of extra go over this problem. We can meet up on Zoom and chat a little bit. So let me know. Otherwise, I'll see you in lab or in an online class here soon enough. All right, later.